Good afternoon. This is Mr. Schweitzer, and this is coming down to one of our, maybe one of our final topics is general idea of precipitation, meaning that will precipitation occur? The basic idea here we want to understand about KSP, and it's a little bit different than other forms of equilibrium because it's just simpler, so we can simplify it, that as you have in larger and larger KSPs, then the stuff that can dissolve can also go up between the two. So if we're doing, let's say, for example, again, it doesn't really matter the name of this salt. I'm using silver chloride. It just doesn't matter. Goes to Ag plus Cl minus. And of course, as if I took another salt, let's say strontium sulfate, then this one would be strontium 2 plus SO4 minus 2. Similar mathematics to this guy. We could do a strontium fluoride, which looks a little different because we got the strontium 2 plus the 2 fluoride negative here. In this case, the KSP would equal the concentration of strontium 2 plus the fluoride squared. So again, as this increases, so does the solubility, no doubt. But this squared here is going to have a, comparison-wise, if you want to make a straight comparison, a correlation, easily could correlate these two together because there's math is set up the same. But this having a square in here just makes it a little more difficult to compare the solubilities. At any point, you could solve for the individual concentrations, and you could answer a question based on who's more soluble. But either way, in this case, what's important to understand is that these values just can't, when multiplied together, exceed KSP. That's what we found to work in lab. Okay, so if by chance these concentrations, did happen for a moment in time to exceed KSP, hence the greater than value, then we would expect the concentrations to decrease via precipitation. Okay. Now, if by chance the concentrations are, and I think I put that backwards there, that this guy is greater than the KSP, then we would have precipitation occurring. So as the concentrations dropped, they would drop until they equaled KSP. And then we'd be at equilibrium. If by chance these concentrations happen to be less than my KSP, all that means is that you are essentially have a beaker with cations and anions dissolved, and either you have a solid on the bottom and it still is in progressing towards being more and more dissolving until I just haven't time-wise reached equilibrium, max point, or simply this stuff just isn't here and I will never have enough. So in this case, we often use the topic what's called reaction quotient. And very often in the past and in various ways this stuff is taught, reaction quotient might be something that is maybe exclusively for this topic. But you really want to stay away from that and understand that it is really a typical cog in any equilibrium process. And you'd want to be able to think of this not in terms of just a tool I use for this process, but it's for any equilibrium reaction. So I'm going to deal with this at first, just kind of discuss in terms of any process. And I have this common little gauge I often draw, which is the concentration of reactants going to concentration of products. And I often state that, this could be, for example, your standard starting place, or STP. And if we started here, then this thing would then be able to approach its whatever desired equilibrium balance that it would have. if it approached this way to achieve a K value, then it would have a K that is greater than 1, because this is a ratio of product concentrations over reactant concentrations. And if it had to go this way to achieve its equilibrium, then the K would be less than 1. And during STP, we don't always think of it, but if you have reactants going to products, the standard temperature and pressure would also equal a 1 molar concentration, not just of the reactants, but also of the products. And it says, okay, ready, set, go. Which way do you want to go? And therefore, your K can be less than or greater than 1, because in that case, if you're starting at 1 molar and 1 molar, now you're starting, we refer to this start, where you're starting, where you currently are, this as Q, or reaction quotient. So what I do is I call the ending Q, and any place else that you are, I may have just said Q, it's K. All right, any other place you are would be called Q. And now I call the STP because it's a typical starting place, but we would just simply call this Q. And it's measured just the way K is measured, exactly the same. So if a Q is 1 molar, then if Q has to rotate towards products to get to K, then we would need to lose reactant and gain product, and this value would have to be greater than 1, because it equals 1 right now. And if this is for a product favored process, not dealing with solubility, this is any reaction. Okay, and then very often, okay, well it says we got if K, when I go to a reactant favored process, then okay, again, as I approach equilibrium, it was 1 and 1 to begin with. Okay, so I need to go to more reactant, so I need to go this way. Therefore, this this fraction has to be less than 1. It has to be, because it started out at 1, and some of my products shifted towards reactants in order to achieve equilibrium. Then yes, I am going to have a value less than 1. So any time I am dealing with something that I'm not at equilibrium, then I often refer to that as the K location. It's calculated exactly the same. And all right, so let's try this with, let's say, silver chloride. I have AgCl comes from Ag plus Cl minus. Okay. Now, depending on how well you think about this, initial amount, stoic ratio, ending. Again, I would like to just take this I out of here and just simply call it Q, because that's really what it is. And there are times I thought I would just every time just replace it with Q, because that's what it is. Not playing a role because it's a solid. And then at this point you could just fill your ice table in as you need be. The way we would work this process is we say, okay, well, I got a beaker, okay, and there are basically 2 versions of this problem. One of them has a little extra wrinkle involved, okay, and I will show the one with the more involved wrinkle first, and then you'll see that the other one is just a little bit simpler. So let's say we have 2 solutions. This is the way this would work out. So I got a solution of AgNO3, and let's say that I have, it is 0.01 molar, and it is, all right, let's say 50 milliliters. And then I got another one that is, let's go with NaCl, also 0.01 molar, and it also is 50 milliliters. In fact, let's go with, let's change this to 0.05 molar. Okay, it doesn't matter, so we'll just do that instead. Now, I want to mix these 2 beakers together into a new beaker. Okay, now I have, in the presence of this new beaker, 100 milliliters. Okay, so I'm increasing my volume. That's important. Adding volume means cutting the concentrations. That would be a dilution, diluting the things. I may have as many ions as I had before, but those particular ions are in a larger volume. The silver ions that used to be in 50 milliliters are now in 100 milliliters. The chloride ions that used to be in 50 milliliters are now in 100 milliliters. Now, at this point, there are two ways, and we try to work on this ahead of time so we can do this skill at this point, but essentially we're doing a dilution, which is M1V1 equals M2V2. Or you can use the molarity formula twice. If you don't understand that, then you need to talk to me. But the initial concentration would be like 0.05. Initial volume would be 50. Ending volume would be 50. No, ending volume would be 100. And you would solve. Now, you might be able to say, okay, we're doubling our volume. I picked nice volumes, they're the same. So I'm doubling my volume. So the chloride concentration in this thing went from 0.05 down to 0.025 moles per liter. And the silver ion concentration, it just equals, well, it doubled again, 0.005 moles per liter. Now those are our new concentrations that we got. So the question is, will we get a precipitation with these concentrations? So we go back to our reaction, okay? The KSP equals the concentration of my silver ions times the concentration of my chloride ions. Now, again, I don't know if we're going to have a precipitation yet, but we want to run this as a Q. Now again, the only difference between KSP and Q is the end result. In the end, these two concentrations will equal 3e to the negative 7th. So because I'm not at the end yet, I'm still working this out, I call it Q, and it's done exactly the same way. I plug in my 0.005, plug in my 0.025, and I run them together. In this case, and again, I don't have a calculator on me, otherwise I would run it through and give you a number, but you plug these two numbers together, and if your Q is greater than your KSP, then you have too much stuff here and precipitation will occur. Now, we like to avoid memorizing. Again, if Q is too small, then we have more stuff that can go in here yet, and therefore that would raise it up to its level of KSP, and we'll have no precipitation because we're not full yet. But again, I don't like to think of things in memorizing, and maybe this is a memorizing version, but I very often would walk through it myself in my brain on the spot and say, well, if Q is bigger than K, all right, then again, this is for any process. Which direction will the reaction shift? Okay, I've already dealt with it in a precipitation sense, but if Q is bigger than K, then Q and K are both a ratio of product concentrations over reactant concentrations. And right now, this ratio is too big, meaning I have too much product and not enough reactant. Therefore, I would, in order to attain K, I would lose reactant and gain product. The way we often would show this graphically or with my little gauge would be a situation where we have reactant concentrations, product concentrations, and maybe my K is somewhere here. It really doesn't matter. It could even be like right here, okay? But this is my K. But I've dumped into this environment a ratio of products and reactants that would be like right here, okay? And now because I'm not at K, I call it Q. And then at given time, indefinitely, this thing might take 1,000 years, but this thing will lose product, gain reactant in a bouncing back and forth process until it squeaks back to K. If I drop in a situation where K is smaller than, if my Q, that's what I want here, my Q is smaller than K, then again it's a ratio of concentration products, concentration reactants, and this thing needs to get bigger. So in this case, what's going on? I don't have enough reactant, and I need more product. Okay, so if this is my location for K, I dropped in somewhere over here. So right here I might be Q. Alright, and in this case, to get to the point where again I will approach K, become K, and therefore I need to lose reactant gain product in order to get that balance of what my K wants, or what the nature is asking. It's just a model replicating nature. So this is a pretty typical problem. The only other version of this that you might see, which is I think an easier version, is if you have, let's say, a beaker, okay, and you have I don't know, a solution containing 0.1 molar NaCl. So really it's a 0.1 molar of chloride ions. And I'm going to dump into this thing silver chloride. But the silver chloride is, let's just say, solid, silver chloride. Let's go with a silver nitrate. Okay? And let's just say it's a solid. So by dumping a solid in here, let's just say my volume of this thing is 100 milliliters. So in this case, my volume is not changing. And that makes it a little bit easier. So I write out my equation. I have AgCl goes to Ag plus Cl minus initial split ratio N not playing a role. In this case, well, this is 0. Okay, this is 0.1. Again, sometimes the data table is easier. It's more useful than others. In this case, I have my little ice table, probably not the most useful thing I want. I'm looking for my reaction quotient. So Q, or KSP, equals the concentration of my silver ions, concentration of my chloride ions. Q is the same thing, except this is where we're currently at. Currently I have a 0.1 molar of this, and they might say, okay, I'm dumping in X number of grams of this item. If they give you a grams of AgNO3, you would convert that to moles, then divide the moles by the 0.1 liters to get the concentration. This is going to be the concentration of the silver ions. And no matter how much solid silver nitrate I drop in, I'm not going to change my chloride ions, which is why sometimes maybe you think this might be easier. An alternate, so that's one type of question. They say, okay, you know, will we have a precipitation if we add 5 grams of AgNO3? Okay. Again, I would determine my concentration of the silver ions, and then I would compare Q to K. Is it bigger? Is it smaller? Is it equal? What is it? Okay. But an alternate question might be this. Okay. You have a solution that contains, all right, 0.1 molar NaCl. Let's just say it is 100 milliliters. And they say, okay, for this thing, the KSP of AgCl is going to be 3.e to the negative 7th. You're dumping in AgCl. Okay, the question is going to be on this guy, how many grams how many grams of AgNO3 can I dissolve? Okay, that's not a problem. Okay, what I do is I say, okay, well, I know that my Ksp equals the concentration of my silver ions times the concentration of my chloride ions. My chloride ions are locked at 0.1 mole per liter. This is 3.0 e to the negative 7th. And I'd solve, okay, well, how much room is there for silver ions? And this could divide out nicely to being 3 point e to the negative 6th, okay, equals the concentration of my silver ions, which would equal the concentration, because it's a 1-to-1 ratio to silver nitrate. All right, and then I'd say, okay, well, this is my moles of silver nitrate. I would say molarity equals moles per liter. Plug your moles in right there. Actually, this is not the moles, this is the molarity. That goes right there. I know that I have 0.1 liters of volume. Solve for the moles and then convert to grams using the molar mass. All right, well, that, again, pretty pretty well within the reach of this class to do a problem like that. All right, this video's gotten long enough. Thank you for sticking it out.